Okay, welcome to the first online exercise session. First of all, my apologies that this isn't live. I'm at home and my internet connection is really bad, so I don't think I can stream for 90 minutes. It's not it's not how I want this to be because I think exercise sessions should be more interactive, so I try to fix something with my internet connection so that I can so maybe we can do it next week or a week after next week live via Teams or Zoom or uh, Instagram Live, whatever. Yeah, but this is the only thing I can do right now, so yeah, we are just doing it. Let's get started with problem 1. You had to show, basically you just had to prove acceptance rejection. So let's get started. Problem 1. Given were x and y random variables with pseudo densities f and g. We had this set x. So the set where f is positive. So that's basically just the support of f. And here's what's different to the proof you had in the lecture for acceptance rejection. Because in the lecture you had that that G dominates F everywhere, and now here G, this is kind of ugly. Here G dominates F only on this X, and yeah, this is a bit different to the lecture. You will see it's no problem. Yeah, but you can't do some things that you would usually want to do. Okay, we had this other random variable u uniformly distributed on 0 to 1, and we had that u is independent with y. Okay, and it was to show that the distribution of x and the distribution of y under this condition are the same. Yeah. Okay. So this is where we start. How do we show that? We just fix some arbitrary x and start with the right hand side here. So the idea is that we just straightforward compute this. So we don't do anything we know from the lecture with these areas the area under F, the area under G. We completely ignore that. We just compute this via base. So we know that well, we just assume that this probability here is positive. Okay. Yeah, this is our approach. What quite many try to do is to switch these two conditions. So to condition on y is smaller or equal than x, and then compute it, which is not wrong, but it's more work. So this is the fastest way, and we will follow the fastest way. But if you did the version of base where you switch the conditions, this was perfectly fine as well. It's just, in my personal opinion, easier to make computations without having a conditional probability. Yeah. So what do we do now? We just look at the two probabilities on their own, starting with number one. We know that y and u are independent. So we know that their probability, their joint probability function factorizes. So we don't have to do some two-dimensional integral things. We can simply integrate twice. So we know that gy. We know that this is our integral for y, and this is our integral for u. Well, we know the distribution of y. This here is the it's the probability density function of y. It's important that you have the L1 norm here, because we only know that G is a pseudo density, so we don't know whether it's whether it integrates to 1. So we might have to scale it, and this is the parameter to scale with. So it's just the L1 norm. So it's just integrating G over the whole R. Yeah. So this is the probability density function of y. The probability density function of u is just the indicator function from 0 to 1. It's because it's uniformly distributed on 0, 1. I skipped the part with the probability density function here. I just wrote it in the integral boundaries. Should be clear. Yeah, so what do we need as well? So we still have this part, which comes into a indicator function. So this u and these y's are lowercase letters. So we integrate over both of them. Yeah, du dy. Okay. And well, what we naturally want to do now is to somehow get rid of this indicator function, because we don't like computing with indicator functions. It's pretty obvious that we yeah, we want to put this indicator function in the integral boundaries. But the problem here, and this is what's different to the lecture, is if we put this indicator function into, well, obviously we put it into the u integral, so into the second one. Well, with our lower boundary, we're good. We just keep it that way. So we just change our upper boundary. The problem here is that we don't know whether this fraction is smaller than 1 or whether it's larger. Because we know that f over g is smaller or equal than 1 from this inequality, but this inequality doesn't necessarily hold on R. So it doesn't necessarily hold on this whole interval. Yeah, this is the problem that we have. Most of you just ignored it, which is well, it's not formally correct, but you will see that it gets to the same result. But to be formally correct, you still have to mention it somehow. But yeah, and here we do a nice trick where we just add another indicator function. So this stays the same, this stays the same. Gy over the norm 1 fy over gy. And we add another indicator function that is gy is bigger than 0. du dy. Okay, so what have I done here? Why does this equality still hold? Well, we restricted ourselves on this case where gy is positive, and we know that gy is a pseudodensity, so we know it's not negative. So what I did here is I restricted myself on the case where the opposite case, which we just we ignored it, we left it. This is a case where g is constant 0. So because we have this g here, the part which disappeared now because of this restriction is a part where we integrate 0. So it's a part where nothing happens at all. And this is the reason why this equality still holds. And the reason why we even want to do it, this restriction, is well, now we actually are allowed to only consider x. And why is this? Because let's look at it. Well, in case well, if g is bigger than 0, when is this fraction bigger than 1? So when is this the case? It's the case when fy is bigger than gy. But the thing is, gy is bigger than 0, and when fy has to be bigger than 0 for this to be bigger than 1, and oh no, yeah, no, I spoiled it. If f has to be bigger than g and g has to be bigger than 0, then f has to be bigger than 0 at y. And when f is bigger than 0 at y, then y is in x. So then y is in the support of f. but we know that on the support of f, this fraction is smaller or equal than 1. So with this indicator function, we actually managed to be allowed to only look at these values being in X. Yeah, and now we are allowed to take this fraction as our upper boundary, because now we know that this fraction is smaller or equal than 1. So this is equal to Fy Gy. Okay, and the rest still remains the same. Yeah, this indicator function is gone now, so we are left with this one here, du dy. Okay, now you see that this part in the integral, the function we want to integrate, it's independent of u. U doesn't appear here, so we just move everything out of the inner integral and just have the inner integral over a constant 1. So we have the norm of g, the indicator function, and then the second integral starts, gy0, but here's nothing else left, du dy, and now the inner integral is super easy to integrate, as you can see. And now what do we have here is gy over the norm. This is this part, and then we have Fy over Gy, which is our integral here, and we are still left with the indicator dy. Okay, yeah, you can see the g's eliminate each other, so what's left is it's just f and the indicator function. Okay, and now we do another trick. We have this f here, and now we make this g into an f. Yeah, why can I do that? It's basically the same reason why I introduced this indicator function. Because if this is true, then f is smaller or equal than g, and yeah, so this holds. Yeah, and well, this looks like it has something to do with the probability of x, what we want to get. So we somehow want to obtain the left-hand side here, which is the cumulative distribution function of x. Okay, so this looks good. I'll keep it that way. Okay, we're done with number 1, with part 1. What do we have to do is to compute this one. Yeah, but we can see these look kind of familiar. So this term is this term. So yeah, the difference between this probability and this probability is this condition. And as you can see, this is just the marginal distribution of this one regarding the first part. So if we just let x go to infinity, then yeah, this is trivial, and what's left is this, which is exactly this probability. And so this is just the limit of our first part if x goes to infinity. So for part 2, we know that f y over g y, that this is just this expression here going, well, if x goes to infinity. So what is here is 1 over g. Yeah, and if this x goes to infinity, then we integrate over r. So we have this, that's an fy positive dy. Okay, cool. So let's look at our big fraction here. So what is this now? And this is by our computations above. This is just well, the norms here, they cancel each other out because we divide it. So this disappears, and what is left are only the two integrals. Yeah, okay. And so we are still left with these indicator functions, but well, what was the reason why we were allowed to introduce them? Because if we look at the other case, at the case we lose due to the restriction, it's 0 anyway. So it doesn't matter if we integrate with this part we left out here, or yeah, whether we do it without. So I can just ignore these indicator functions here and here because it doesn't change the integral. So basically what I have is this divided by this. Okay, but this part here is just the L1 norm of f, as you can see, which means that our expression here is fy f1 dy, and well, this is now this is the pseudo density of x, and by dividing through the norm, this is the density, the probability density function of f. So yeah, what do we have here now? We have here the CDF of x, which is exactly our goal, because here this is what we wanted to show. And since our lowercase x was arbitrary, yeah, it's true for the whole R. Yeah. This was exercise 1. Right. Let's get to the second problem, where the task was to prove Mazalia's polar method. So what many of you try to do, and what you will find in Professor Neunkirch's solutions online, is it is possible to reduce the problem of proving Masalia to showing that you can get from Masalia to Box-Mueller. And well, in the lecture, you proved that Box-Mueller is a valid method to generate Gaussian variables. So if you can show that it's equivalent with Box-Mueller, then you're done. Yeah, many of you tried to do. Well, many of you did it. It's in the solutions on Ilias as well. The idea is just to do some transformations or substitutions. Which substitutions? Yeah, you have many options actually. So if you're interested, just look at Ilias. But there are other ways than on Ilias with other transformations. And yeah, what I'm going to do now is to give a well, to do something else, because I'm going to give a complete proof of Masalia in the way that you don't need Box-Mueller for that. So the proof I'm going to show you now is independent of Box-Mueller. You don't have to know that Box-Mueller exists or is true to make this proof. Yeah, this is what I'm going to do now. Okay. I think I made that point in another exercise session already, but be careful what you claim, and then what assumptions you make to prove this claim, because I saw it quite often on the homeworks, that you just claimed, well, that you assumed the claim you wanted to prove, which is, from a logical point of view, just not meaningful. So if you want to show that something is Gaussian distributed, please don't assume that it's Gaussian distributed, because this, yeah, it's just not meaningful. So the calculations were right most of the time, but it's just a little technicality to begin with. Be careful with that. Okay. So what I'm going to do in this proof is I will assume two Gaussian variables, and then I'm going to show that they have the same law as these as this expression you have in Masalia with the two uniform random variables. Yeah. Okay, so let's get started. Let x and y be independently Gaussian, and g a bounded measurable function on R2 to R1, but that's quite obvious, right? Okay, and we start with the expectation of g of x and y, and we, yeah, if we show that the expectation is equal for every bounded measurable function, then we know it's equal in law. Yeah, so this is okay. Let me write this quickly up here. What we want to show, if x and y are IID Gaussian, then rho u and rho v are IID Gaussian for this rho and u and v as in Masalia. Okay, so this is what we are going to do now. And we do this by showing more or less that the expectation of g of this is equal to the expectation of g of these two. Okay, we know that x and y are Gaussian, so we know, and they are independent, so we know their joint probability density, which lets us write this expectation into this gxy exponential function of x squared y squared, right? Yeah, right. Dx dy. Okay, and now you will actually see why this method is called Masalia's polar method, because now we transform our problem from the Cartesian system in which we are right now into the polar system. So by this standard analysis 1 or 2, I don't know, polar transform, which is x is cosinus phi and y is sinus phi. So dx dy is r d phi. I'm not going to show this. This is yeah, you know how it works. So just the determinant of the Jacobian matrix of these functions here. Yeah. But this is, I think this is pretty common knowledge that it's just R. Okay, so what do we have now? This stays the same. Yeah, if you do transformations, be careful about the integral boundaries. In this case, it's these two. You can check that if you want to. I'm not going to show it. It's just yeah, you can see pretty easily that it's right. Okay. Sinus phi expectation of minus r squared 2. This r squared is because we have well, this squared plus this squared plus this squared is this trigonometric trick where you get one out of these two. Yeah. Oh, can't forget the r, dr d phi. Okay. Well, what we're doing now is we are making a substitution to make life a bit easier. What do we substitute? Z to the power of 2 is now expectation squared 2. So we just want to get rid of this part. Oh, I forgot a bracket here. What else do we do? Yeah, this is just our substitution we make. So what do we know about what changes here in the integral is just 2 z dz is minus r expectation of minus r squared over 2 dr, and we also know from the first line here, if we look at what r is, we know that r is minus 2 log z squared. Yeah. So now with the log and the trigonometric functions, it already looks somehow like Box-Müller, but so if we wanted to apply Box-Müller somehow, this should be the point where we do it. But as I said, we are not going to do it. We are going to do it without Box-Müller. So, well, what is this? With our substitution we made, it's 1 over pi. The 2 disappears because of this 2 here. 2 pi 0. Yeah, be careful about the integral boundaries again. 1 0 g log z squared cosine phi minus 2 log z squared minus phi z dz d phi. Okay. Well, I think I made a mistake here. I think I messed up the boundaries. Exactly what I said to be careful about. I think we need to switch these two. Yeah, be careful there. Mistakes happen. But I think this should be okay. But think for yourselves. If you find a mistake, let me know. Yeah. Okay, so we then make some computations. 2 pi 0. Because we now want to do another transformation, and for this, it's useful to have z squared here, because, well, if you look at what we want to show, we have this part we needed. Yeah, but where do we get this z, we just insert another one here. And we do the same thing in the other argument, log z squared sinus phi z dz d phi. Okay, and then we are done with the polar coordinates, and we switch back to the, well, we transform it back to the Cartesian system. So we basically just do this the other way around. And what we get now is well, let me introduce some new things. This b, I will define it, and another function rho uv times u, and rho uv v du dv, where well, b1 is just the unit ball in R2. So b1 is simply every pair in R2 such that u squared plus v squared smaller or equal than 1. So just the standard unit ball. Yeah, and our function rho is exactly what we need for Masalia. So it's u squared plus v squared log u squared plus v squared. Yeah, you can check it. It's true. Yeah, you can see the analogy, and yeah. So this is basically, well, here we can see now that it has some resemblance to Masalia. But we still somehow, well, at this point, u and v are just numbers. We have nothing. We have no random variables to work with at this point. For Masalia, we want to have some uniform numbers. And well, we have this unit ball here, and the idea is now we cover this unit ball with a two-dimensional uniform random variable. So we now just look at two capital letters here, because now we have random variables. We look at two minus one uniform random variables. The idea is we have this b1, so we have yeah, this beautiful unit ball, and we somehow want to integrate over it. So the idea is this standard Monte Carlo hit or miss integration thingy, where we just have uniformly distributed random numbers here, and yeah, that's basically the idea. Well, it's quite informal here, but I hope you get the point. Okay, and what do we know about this random variables now regarding this unit ball? Well, you might see it already here, the probability that this pair UV lands in the ball is just pi over 4. So yeah, where does this equality come from? It's just the area of a circle and the area of a square. So circle, square, yeah. Okay, so we have this now. Let's get back here. Yeah, what is it? So we have this 1 over pi here, and we have this pi over 4 here, and we want to sneak this probability into this formula. So what we do is we do this is equal to the probability uv is in B1, which is pi over 4. So 1 over this 1 times 1 over 4. So you can see this is 1 over pi. So we got from this expression to this expression. And now, because we want to do something with these random variables, and well, it's no coincidence that these are called u and v, and we have a u and a v here because we use it now here, and we don't look at this unit ball anymore, but at this square. So we integrate now over this set. Well, of course, we have to restrict ourselves still on the unit ball, which we do here. Here we have lowercase letters again, because now we're inside the integral. G rho uv times u, rho uv times v, du dv. Okay. Well, what do we have here now? What is the joint probability distribution of these two? Well, because we have this larger than normal interval, the density on this interval is 1 over 2 for both. So the since they are independent, their joint distribution factorizes, and their joint probability distribution function is just 1 over 2 from the one variable times 1 over 2 from the other one. So this 1 over 4 is actually just our joint probability density function of these two guys here. Which is cool because now we have here a expectation, which has something to do with these two random variables here. And well, we have still this condition here. So let's see what do we have here. We have p uv in the unit ball times the expectation that of g rho uv. Now we have the capital letters again because these are our random variables up here, these two. U rho uv v. Well, we still have our indicator function. I just copy pasted here. Okay. Now observe that this indicator function, well, this event here is exactly the event we are looking at here. And well, I don't know whether you did it in stochastic 1 or stochastic 2 or something like that. But if you look at conditional expectations, yeah, okay, the general formula for conditional expectations, well, we have some random variable y conditioned on the event b, and the conditional expectation is just the expectation of y times the indicator of b over the probability of b, which is exactly what we have up here. So this is a general formula. So yeah, p has to have some mass here, of course. But from this expression, and when we look what we have up here, we have just the expectation of g rho uv times u rho uv times v conditioned on u squared plus v squared smaller or equal than 1. And well, if you look at it, this is exactly what Marsaglia claims. So we condition these two uniform random variables, which are on -1 to 1. We condition them to be in the unit sphere. Yeah, and then well, if we condition it, then this expression is equal to this expression, and we know that x and y are independently Gaussian, so we know that these two guys, so this and this, conditioned on this event, are independently Gaussian as well, because we have shown this for every measurable bounded function. Yeah, and we are done here. We have proven Marsaglia without Box-Müller or any auxiliary result. Yeah, which is quite nice, I think. You can see it's not that long of a proof itself, so I can show it to you. If you want to write it down, just pause the video or something like this. It's really not that long. You just have to make this transformation into the polar system, then one substitution, then transform it back, and you're done. And this is, yeah, this might be even shorter than the version where you show that it's equivalent to Box-Müller, because you have to show quite a few things there as well. Yeah, so this is it. It's, yeah, I think it's even quite easy to remember what you have to do here, because well, the only clever thing you do is do a transformation to the polar system, and well, it's called Marsaglia's polar method. So what you do is already in the name. But yeah, just my personal opinion. If you do it with Box-Müller, it's perfectly fine as well. Okay, so we are done with problem 2. Problem 3. This was some measure theoretical stuff. Well, at least it went into the direction of measure theory a bit. Because there was some confusion there, and because everything with measure theory is confusing, I am going to start with a small intermezzo of what is a random variable. Well, our general setting here, let x be a RD valued random variable on our probability space omega a p. We have an a from script a. We can just assume right here that it has some probability mass. And now what we consider is this, it's a probability measure, but we have to show that first. This W, which is defined by X in B, conditioned on A, where B is in Borel R to the power of D. Okay, and let me just quickly do a reminder what means RD valued and what means on this probability space. So a random variable is just a function from something to, let's call it something, which is measurable. Okay, this was super vague what I just said. So we have two measurable spaces. This one, we know it from our probability space here, and another one. Both are measurable spaces, and they have in general nothing to do with each other. Okay. That being said, this one is called the sample space, and this one is called the state space. And well, if we say that this is RD valued, then we mean that our state space is R to the power of D, endowed with a good sigma field for this space. So if this E is if it's R, then the sigma field, the corresponding sigma field is the Borel sigma field. If this is N or some countable set, then this is the well, if it's N, then it's the power set of N, something like this. So when the problem set when it says that X is an RD valued random variable, it means that it maps into RD from omega. And the thing is now that this probability measure takes, well, it is defined on this sigma field. So you can take an element of this sigma field and measure it with this probability measure. But if you take an element of this sigma field, well, at first you can do nothing with this probability measure because they might be incompatible. Because, well, this, if we talk about random variables, this is mostly something with numbers, and this is mostly something super abstract. So, yeah, this is what's the general problem here, and this is what was kind of confusing, I think. Okay, and well, what we want to show is that W is a probability measure on RD Borel RD. So we want to show that well, W is defined on this measurable space, and we want to show that it's a probability measure on this measurable space. So this W has nothing to do with, well, it has indirectly something to do with this measurable space, because this P is this measure defined on this space, but W cannot take elements of, well, this W cannot measure elements of this sigma field. That's not how it's defined. Okay. This was some general remark on the whole measure thing here, because it, well, quite many of you got confused there, and it is confusing. I don't deny that, but always keep in mind what you want to, in which space you currently are. So yeah. Well, with a picture, we have this omega. This is our sample space, and we have our state space here, and X maps from omega to E, and well, we have here this sigma field, we have here this sigma field, and P takes values in here, and P doesn't take values in here. But W takes values in here. So W takes values out of this sigma field. And so what do these two have to do with each other? So, well, if we do it unconditionally, so we ignore this A here, then we just look at the image measure of X. So we have this P, and we look at the image measure of X regarding this P. This is just our distribution of X. So our distribution of X is defined here, but it's defined as the image measure. So indirectly we land in here. But well, if we denote the distribution as this this thing, it takes values in here, such as W has this in common with px. It takes values in here, and it somehow transforms it into values in here, and then we can measure it with this p. But this is a stochastic one, or measure theory. Yeah. But that's the idea. And yeah, as I said, W is in here. So W is yeah, it's the conditional distribution of X. So it's again a distribution, and it's again somehow an image measure. Well, not exactly, but yeah, that's the idea. Okay, let's get to the exercise. Verify that W is a probability measure. Okay, what do we do now? Yeah, when is it a measure? So we want to show that if we put the empty set in here, that it's 0. Is it 0? Yes, it is. It just follows from P being a measure. So we compute that this is P, X is in the empty set conditioned on A. Yeah, which is by base. P, X is in the empty set. Intersected with A. Okay, and here is where it gets a bit confusing again with measure theory, because well, this empty set is an element of our epsilon, so of our sigma field, in this case Borel RD, but it's in our state space. And as I said, P measures the sample space, but the thing is, this set is, this empty set is in epsilon, but this set is actually in script A, because it's always kind of confusing, but this is a short notation for X omega is in the empty set. So this is what this set means, and here it's more clear that this is an element of the sigma field of our sample space. Yeah, so this is the reason why it's meaningful to have this intersection here. Yeah, because it's measurable, because X is measurable, this part here is just probability of the empty set divided by the probability of A of this event. And yeah, because P is a measure, we know that P of the empty set, now the empty set, well, this one is in epsilon and this one is in A. And yeah, this is 0. This is 0 because this is a measure, so it's 0. So check. Yeah. Second thing we need to show for W being a measure is sigma additivity. So we take a sequence of pairwise disjoint sets A1, A2, and so on in Borel RD. Here, many of you said they are in A, which is not quite right because of the reasons I explained here. W is a measure on this measurable space, and yeah, A is here on this measurable space, so we can't compute elements of A with W. So we look at a sequence in the sigma field of our state space E here, and this is its sigma field, where the sequence, the sets have to be pairwise disjoint. Okay, and we want to show that W of the union of these AI is the sum of W of AI. Okay, yeah, again follows from P being a measure. So this is just P of x in e gleich 1 AI conditioned on A, which again by base is P over x I equal to 1 AI intersected with A over PA. Well, what can we do here now? We try to move this one out now. So what this is where we intersected with something here, and this is disjoint. So the intersection of the particular sets here, the intersection with this, they are still disjoint. So what we have here is that the union's still disjoint of x is in AI intersected with A. Yeah, we have this equality here. Yeah, and again, P is a measure, so it is sigma additive. So this is true. X is in AI conditioned on A over PA. Yeah, we can see that this thing is W again. Well, we just repeat this step here. Sorry. So we have and this is what we wanted to show. So we are done here as well. And from 1 and 2 follows that W is a measure. Okay, but we had to show that it's a probability measure. So the question remains whether W of RD is 1. Here again, it's W of RD and not W of omega. But if you wrote omega, I didn't subtract any points. So it's really hard to go into a measure theory lecture at our university. So most of you didn't do it, I think, and yeah, these things just happen. Okay, so why is this true? Again, follows from the fact that P is a probability measure. We have P of x in RD conditioned on A. Again, with base, we have x in RD intersected with A over PA. Well, this is trivially true. So this is a subset of this set. A is a subset of this, which means that if we intersect it, just A remains, meaning that we have this equality, which is 1. Okay, nice. We have shown that W is a probability measure. Cool. Yeah, this is the first part of the problem 3. Okay. Second part, let D be equal to 1. Quickly write it down. Let D be equal to 1. So we are just now in R. So our state space is just R. And let A be well, on the problem set, it's this notation, X in A, B. If this confuses you, this is, well, you can abbreviate this with just X in A, B. Yeah, here the right-hand side is a more common writing, I think. So don't let yourself confuse with this omega. Okay, what do we know? Well, it is the assumption that A is strictly smaller than B is quite obviously necessary. So A, B, pretty standard, and it is another condition that we have some mass on A. Okay, so this is where we start. Modify the ITM for sampling X to obtain a method for sampling from W. Okay, so quick recalling, what was ITM? We have a cumulative distribution function from X, say F. F is the CDF of X, meaning that it's the CDF of the image measure, also of the distribution of X. And then we look at the pseudo inverse, and this is the ITM for sampling X. So what we want to do now is sampling from W, and we do this in 2 steps. Step 1, what is the CDF of W? And step 2 is what is its pseudo inverse. Okay, these are the 2 steps we need to do here. Starting with 1, well, we just look at some X in R and W in minus infinity to up to X. So we want to compute this because this is the CDF of W. Let's call it G. Okay, so look at some different cases. For X smaller than A, what happens there? We know that X smaller than X conditioned on X is in AB, because this is our A from the definition of W. Well, if X is smaller than A, and we know that X is, well, that the realization of capital X is bigger than A, then the probability that the realization of capital X is smaller than X when X is smaller than A, well, it's 0. Because it's just yeah, it kind of contradicts itself here. For x bigger or equal than b, we have that x smaller than x in a b. By base, this is 1 because, well, if we know that x is in here, then we know that x is smaller than b, and x smaller than lowercase x, when we know that x is already smaller than b, which is smaller than x. Well, it's trivially true, so it's 1. Yeah, it gets interesting in the middle. For x is in a b, what happens here? Again, we do base x conditioned on x is in a b. Yeah, from base we just know that x is in ax. This x comes from the fact that this a comes from the fact that smaller case x is in a b. Yeah, here. Yeah, so we just here we have x is in minus infinity to x. Here we have x is in a b. From base we know that here we have to intersect these two, and the intersection is just the part from a to x. This is what we're doing here. Yeah, here we still have a b. Okay, but now we just have the unconditional distribution of x, and well, we more or less know what this is because we have this f as the CDF of x. So we can express this term with f, which is just fx minus fa divided by fb minus fa. Okay, so this is nice because well, out of these 3 cases, we can build ourselves the CDF of W explicitly, because this here is now well, let's look at it. Case 3, if smaller case x is in a b, well, then we are in this case, so fx minus fa over fb minus fa. Yeah, if you are in case 2, then it's just 1. So we restrict ourselves on case 2 here. Bigger or equal than b. Yeah, it's 1 in this case, so we can just leave the indicator function here. Yeah, and in the first case, well, if it's less than a, then neither of these indicator functions admit 1, so it's 0. So it's what it's supposed to be. We're good. This is the CDF of W, which was the first part of the exercise of the problem. Okay, now the question is, what is the pseudo inverse of this one? Yeah, quick reminder: the pseudo inverse, let's call it I of g, is some function from 0 to 1, mapping on R, where it maps y on the infimum, where g of x is bigger or equal than y. Yeah, this is the pseudo inverse. Okay, let's look at the boundaries. There's always something special about the boundaries. So what happens when we insert 0? Well, if we insert 0, yeah, let's look at it. Then we know that the x we are talking about, well, it must be g on evaluated at this x must be bigger or equal than 0, but we know that g is a CDF, so it is non-negative, which means that it's minus infinity, because yeah, that's just a property of CDFs. Yeah. Okay, this was the first part. Second part, what happens when we evaluate the pseudo inverse at 1? Okay, let's look at it. What is the smallest value we can insert here that this admits 1? So obviously one of these two indicator functions must be triggered. If the second one admits 1, then we have 1. So we know that this is smaller or equal than b, because if this is b, then we are in this case and we have 1. The question is, can we get some smaller x, letting this admit 1? So let's look. Can this be, when is this expression here 1? So obviously when it's b, when x is b, then it's 1. And can it be 1 at some other value? No, because well, this is an increasing function. So we know that this is b. And now the question is, we have this case, we have this case. What happens when y is between 0 and 1? So yeah, as we can see here, if y is between 0 and 1, it must be, well, what happens in this part, because well, this is only interesting for y equal to 1. So what happens here. So the question is, yeah, g is just this fraction now, in this case. So we have y is smaller or equal than fx minus fa over fb minus fa, which is okay, what have we got here? Fx is bigger or equal than fa plus y fb minus fa, right? Yeah, should be right. Okay, but we are interested in x, so we have x in here. What do we do now? We evaluate all this on the pseudo inverse of f. So because the pseudo inverse is monotone, we can apply it on both sides and nothing happens to the inequality sign. So I of f of x is bigger or equal than no, I of f of a plus y fb minus fa. This one. Okay. Yeah, it's a general fact from it follows directly from the definition of pseudo densities that this one here is smaller or equal than x, I think. So now we have our x here. And recall that it's the, well, here we look for the infimum of x satisfying this condition. Yeah, what's the infimum here when it's equal? So what we know now is that in this case, if we are in this case, that the pseudo inverse of G is just equal to this. Okay, cool. Yeah, so we have these three cases. So we can give an explicit formulation of the pseudo inverse of G, where G is the CDF of W. So the ITM for sampling from W is just the normal ITM algorithm, but not with the pseudo inverse of the CDF of X, but this pseudo inverse. So it's the same algorithm, but just this function. Yeah, and this is it for the exercise. Oh, we got a problem 4, but this was just MATLAB, I think. Implement, generate, use MATLAB. Yes. Okay. Compare the running times. Okay. On the, in the solutions, well, for the code, just look at Ilias. The code will be uploaded there. For the efficiency of these methods, Professor Neunkirch has in his solution on Ilias has this order that rand n is by far the fastest, which makes sense because well, the people at MATLAB are getting paid to be fast, and well, this is what they thought is best. Then Box-Mueller, then norm inverse, so just ITM or what this is, and then Masalia. So this is what Professor Neunkirch states in the solutions on Ilias. If you look at literature, you often find the claim that Masalia is faster than Boxmüller, so that Masalia is faster than Boxmüller theoretically, because the idea is that that for Boxmüller you have to evaluate log, cosinus, and sinus, and for Masalia you just have to evaluate log, and this well, these trigonometric functions are time consuming. So in theory, Masalia should be, well, yeah, the literature claims that in theory Masalia should be faster, but the thing is, in Masalia you have to generate these random variables, this uniformly distributed random variable on the unit ball, and this is not that easy. Well, it's easy to do, but it's not that easy to compute actually. So if you make a really fancy generation of this random variable, then in fact Masalia is faster. But if you don't really care about this, then well, if you just quickly implement it, then Boxmüller is faster, because this is quite time consuming by itself. Yeah, but if you looked into a book or something like this, and there was that Masalia is faster than Boxmüller. Actually, I sent some emails where where I claimed that as well, because I learned that in stochastic simulation. Yeah, this is the reason Masalia doesn't have the trigonometric functions, but Masalia has this a bit awkwardly distributed uniform variable. Yeah, that's the reason why in the solutions on Ilias this order is written, and most of you actually got this order as well. Okay, yeah, this is it. I'm a bit over time, I see, but yeah, it's a video, just fast forward. We get the 90 minutes. Yeah, if you have any questions regarding this exercise sheet, this exercise, or any other exercise or MCM related stuff, just write me a mail. If you want a Q&A session for the exercise sheets, then I hope that I can provide some live thing soon in the future. Yeah, if not, I think when before the exams, we can do a live Q&A if you want that. Yeah. In the meantime, if you have questions, feel free to write me a mail. Yeah. So if give me feedback about this format of exercise. If I am too fast or too slow, or if it's too boring, if I should write more neatly, something like this, just just give me feedback, because I have never done this before. I don't know it. Yeah. Okay. Great. Then this is it. Yeah. see you next week or something like